The reason why we care about linear dependence or independence is because we are thinking about our equations as vectors, as lines. And whether or not our equations, vectors, lines, etc., are linearly independent tells us what types of solutions we might have, or what the potential is for a solution to have. So the next thing to talk about is span, and span is a little bit more theoretical of a concept, but I have this table here, and I hope some of this makes sense. If not, that's fine. Follow the rules on the table. So here's our theoretical mathematical statement. If S is a set of vectors, think about this as if we have equations. If S is a set of equations. The subspace that consists of all linear combinations of vectors is called the spanning space. Essentially, this is where our B vectors can live to have a consistent system. So the subspace, that's what it's called, the spanning space. It's just a ND space, a space that exists, that can contain our B vectors. So the subspace that consists of all linear combinations of vectors is called the spanning space, and we say the vectors span the subspace. So just work with me, we'll follow the table. So if I have vectors that live in R2, so these are vectors that consist of two numbers, 1, 2. If I have a set of vectors, and there is one linearly independent vector in that set. So essentially, if I have 1, 2, 2, 4, 3, 6, 4, 8, all of these are dependent. They're dependent on each other. They're just multiples of the other. So I multiply this one by 2, this one by 3, by 4. So they're dependent on each other. So if I have a set of vectors and only one of them is independent, then they span what's called a line. So all of these exist on the same line. If you draw them graphically, it'd be that one, then this one, then this one, then this one. Which means that my B vector also needs to exist on this line. So all of my vectors are collinear. Which means if I use two of these vectors to create a system of equations, then my B vector also has to be on this line. That's what that means. So these set of 4 vectors span a line in R2, or span a line in 2D space. If 2 of them are independent, so if I have 1, 2, and 4, 3, these are not dependent on each other, and if I draw them, it would look something like this. 1, 2, and 4, 3, something like this. Obviously not the same. But no, they're not collinear. They're on different lines, which means that any B vector that exists in 2-dimensional space will give me a consistent system with one solution. So here, I have an infinite number of solutions because I only have one piece of information. Here, I have 2 independent pieces, so that means I can have any B vector, can exist anywhere, it can be here, 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 it can even be here or here, which means that these 2 vectors span a 2-dimensional space, which means I can get a B vector from anywhere else in 2D space in R2. So they span a 2D space in R2. 2 vectors, they're non-parallel. Okay, that's 2 vectors in R2. Let's look at vectors in R3. So in R3, I have 3 options. I either have 1 independent vector, 2 independent vectors, or 3 independent vectors. So I have only one piece of information repeated multiple times. Here I have 2 pieces of information. Here I have 3 independent pieces of information. If I only have 1 piece of information, it only spans a line. Same thing like it was over here in 2D space. It's just anything along that line. As long as I have anything along that line, I'm good. If I have a B vector along that line, that's fine. I'm going to have an infinite number of solutions as long as it's on that line. So these 3 vectors span a 1D space, in R3. If I have 2 pieces of information, 2 pieces of information, that means I have 3 vectors or vectors that are in the same plane. Which means rather than it being a line, it's a plane. So essentially a 2-dimensional space. Which means that I might have an infinite number of solutions as long as my B vector is also in that plane. So they span a 2D space in R3. If I have 3 vectors or 3 independent pieces of information, then it turns out that my B vector can be anywhere in my 3-dimensional space. They span a 3D space in R3, or all of R3. We can follow this pattern for R4. If there's R4, I have 4 options. If I only have 1 piece of information, 1 linearly independent vector, it spans a line. If I have 2 pieces of information, 2 independent pieces of information, it spans a 2D space in R4. If I have 3 pieces of information, it means it spans a 3D space in R4. And if I have a 4 pieces of information, independent pieces of information, it spans all of R4, or a 4D space in R4. So given however many pieces of information I have, how many independent equations I have, I'm going to have an infinite number of solutions or a unique solution as long as my B vector exists in my span. So if we go back up to our first set of examples, so if I look at this one, these are 2 linearly independent vectors. The B vector can honestly come from anywhere. This one comes from here. It could be here, 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 here. It doesn't matter where my B vector is. I'm going to have a unique solution. For here, consistent infinite solution, I have only 1 piece of information, 1 independent vector. My B vector, as long as it's on that same line, I'm going to have a consistent solution. There's an infinite or a consistent system. There's an infinite number of solutions, but a consistent system. Here I have the same thing. My 2 vectors are collinear. There's 1 piece of information, but my B vector is not on that line. My B vector did not come from the space, the spanning space of my X and Y vectors, so my system is inconsistent. So the concepts in this section are much more heavily theoretical. But essentially when it comes to span, what we're going to do is first we find the number of independent vectors. Number of independent equations we have essentially. And then to find the span, we say the vectors span a blank D space in R blank, where this first blank is the number of independent vectors. And this blank is the number of elements in the vectors. This is very theoretical. So if we look back over here, if we look at that formula, if we have 2 vectors in R3 that are linearly independent, they span a 2D space in R3. 2 linearly independent vectors, each one contains 3 numbers. And that's span. We will look at some examples of this, but essentially follow that formula. The vectors span a blank D space in R blank. The number of independent vectors and the number of elements in each vector.